are called to our national forests for many different reasons. A closer experience with nature, the exercise and pleasure of mountain biking, the excitement of off-road driving, the challenge of hunting. For whatever reasons or mode of travel, they all use a Forest Service trail. Trails are the pathways to the national forests of the United States. They allow us the freedom to get away from it all and enjoy the great outdoors.
Trails also protect nature from overuse. By funneling the foot, hoof, and vehicle traffic onto designated trails, we limit the heaviest impact to these small strips of pathways and reduce the damage to surrounding areas.
But there is a price to pay for the convenience and advantages of trails.
Boy, this trail's a mess. Suppose we should talk to Greg about relocating it?
Yeah, looks like most of it.
Trails interrupt surface water runoff. Whether on steep or flat slopes, once the natural flow is changed, water will create a new pattern, and it will take the easiest path, often down the cleared trail, removing soil and destroying the tread. Erosion happens in all climates, in mountains or deserts, in a variety of vegetation and soil types, and on trails with heavy or light use. Severe erosion can occur during violent thunderstorms or during spring snowmelt in areas with heavy snowfall.
But if we can divert this surface water off and away from the trail, it won't build up to an erosive force. To prevent water erosion, proper design, location, construction, and maintenance of the trail are essential.
There are some basic structures, construction or reconstruction techniques that will deflect surface water off the trail.
If properly installed and maintained, these structures and techniques help prevent and control trail erosion. The first technique is the grade dip. This dip in the trail diverts the water to the outside and off the trail. Grade dips are most effective on stable soils on grades under 8% and work best when incorporated into the original trail design and construction. Create a grade dip by excavating a dip 6 inches across the trail bed at a sharp angle, usually 45 to 50 degrees. The dip should be slightly outsloped or lower at the water spill point, so water flow off the trail is uninterrupted. Outslope the dip 3/4 to 1 1/4 inches for every foot of trail width. Once you've completed this shallow ditch, feather the trail into and out of the dip on either side. Feather the trail from the dip upgrade approximately 10 feet and downgrade approximately 3 feet. The downgrade section actually has an opposite grade to the prevailing grade of the trail. This way, the water can't flow past this point and flows out at the spill point. Generally, the length of a grade dip ranges from 10 to 20 feet, but may be as short as 5 feet. Depending on the amount of runoff, it may be necessary to construct a rock spillway at the end of the grade dip to prevent erosion at the water spill point. Drainage dips are constructed by using the excavated soil to create a mound on the downgrade side of the dip. However, constructed grade dips are preferred over excavated drainage dips because they hold up better under stock and wheel traffic. To install a drainage dip, shovel the soil from a 6-inch deep trench onto the downgrade side of the dip, making a 6-inch high mound. The mound should be smooth and well compacted so stock or wheeled vehicles won't cut through it. Feather the trail upgrade of the dip approximately 5 to 10 feet. Grade dips can also be used in a minor stream crossing to prevent the stream from running down the trail. In this case, construct the dip in the same manner as before, keeping in mind that the downgrade side of the trail must be at least 12 inches above the high water level. A rock spillway may be required. As we mentioned earlier, grade dips are generally used for grades under 8%. They're not recommended for trails with grades over 12% because the trail at the grade dip would be too steep. With a new trail, the grade dip can be flagged and staked properly where soil and water movement is of concern. There's usually enough variation in a trail that the dips can be worked in even at a steady 10% grade. Outsloping should run the entire length of a trail and is most effective when used in combination with grade dips.
We mentioned outsloping briefly during construction of grade dips. Basically, outsloping means that the outer side of the tread is lower than the inner side, allowing the water to run off the trail. If a trail is constructed correctly, maintained at proper intervals, and no unusual factors exist, outsloping the tread is a good technique to divert surface water. Outsloping should run the entire length of a trail and is most effective when used in combination with grade dips. The grade of outslope must be greater than 2% to effectively drain the water from the trail surface. And in most cases, the maximum grade of the outslope is around 8%. Any steeper than that, and the tread becomes hazardous when frozen or snow-covered or during wet periods. Horses tend to prefer walking on the outside part of a trail, and bicycle riders like to keep their inside pedal away from the hillside. Rocks installed 2 to 3 feet apart will keep this traffic from breaking down the outside edge of the trail. The rutting effect of stock and wheels tends to create grooves in the trail. This forms a berm on the outside that defeats the outsloping and leaves the water on the tread. Water flow from seeps and springs may be too large to be moved off the trail by outsloping alone, and slough materials from the upper bank may build up the inner edge of the trail. To maintain an outslope trail, pull the slough and berm back into the trail, and then regrade the trail.
A water bar is a rock, a row of rocks, or a log laid at an angle across a trail to move water off the trail tread. A water bar isn't necessarily the best way to deal with surface water, but it's often needed when a trail is poorly located or has a grade that's too steep over a long section of trail. Although water bars are the most commonly used method for erosion control, they should only be used after grade dips have been ruled out. In some cases, especially for reconstruction of a trail or for steep trails, water bars may be the only option. The first step in water bar construction is to determine the location. There are several different elements to consider. First, the water bar must be located to fit the individual characteristics of the site. It should be as near as possible to the top of a pitch grade, or as close to the source of the water as possible, to reduce the amount of damage the water will do to the trail. Second, avoid locations where a long outlet ditch is required. Third, don't put a water bar where it'll discharge onto a steep, erodible slope or back onto the trail below. Fourth, water bars should discharge onto a filter area. And fifth, a water bar should be near a turn in the trail or at the end of a switchback, so the flow of the water can go straight as the trail turns away. With these considerations in mind, determine the proper spacing. Water bars must be close enough so water accumulation doesn't cause appreciable erosion. There are several variables to consider. The grade of the trail, type of soil, amount of runoff, trail use, and opportunities to move water from the trail surface all play a part in determining the spacing of water bars. Heavily used trails often need closer spacing because traffic loosens tread material, which may increase erosion. Trails in areas with intense snowmelt runoff or severe thunderstorms may need more closely spaced water bars. Obviously, these variables differ from forest to forest. Consequently, each forest needs a spacing guide based on local soils, precipitation, and use. This water bar spacing guide was developed for areas with both fine and coarse-grained granite soils. For example, if the trail gradient is 5%, the water bar spacing in a low erosion area should be 300 feet. In a high erosion area, 150 feet. At 15%, this changes to 100 feet or 50 feet, depending on the erosion factor. Once you've determined where to place a water bar, move on to installation. The two major materials used for constructing water bars are logs and rocks. A rock water bar is preferable to a log one because of durability. Rocks should be rectangular and narrow. Unfortunately, properly shaped rocks are seldom found near the trail, so you'll either have to haul them in or use logs. Treated logs are the best substitute for rocks, but require pack stock or motorized equipment to bring them to the trail site. Of course, you can also use natural logs cut near the trail site, but if the cost is reasonable, treated logs are preferred and will last much longer. Just be sure to treat any new drill holes or cut ends during the installation process. If you're using a log cut at the site, peel off the bark and use a species that is resistant to rotting.
Good. We got her here, huh?
With materials chosen, the water bar is ready to install. Begin by digging a trench that's 1/2 to 3/4 of the depth of the water bar at a 40 to 60 degree angle to the trail tread. To determine this angle, lay a tool across the trail and mark the end point with the end of the handle. Next, pivot the tool approximately 90 degrees and mark the other end. Now scratch a line in the dirt connecting both points to create a 45-degree angle. At this angle, the water can flow straight and will carry the sediment off the trail instead of slowing and depositing it along the way. If the excavated material is clean soil or gravel, place it on the downhill side of the water bar. Don't disturb the tread on the downhill side of the water bar. It provides a solid support for the log or rocks. When using rocks, they should overlap like shingles, so the water moves toward the outlet drain. If using a log, it should have a minimum diameter of 6 inches. Place the peeled log into the trench. Bury the log at least a foot into the hillside. Cut the lower end so it extends no more than 12 inches past the outer edge of the trail. The water bar is now ready to be anchored.
There are regional differences in the preferred material for anchoring water bars: rebar, wooden stakes, or rocks. Each has advantages and disadvantages. Rebar isn't as much of a tripping hazard as stakes and rocks. However, if the log wears down, it can become a problem if stock step on the exposed rebar. Rebar is often the favorite choice in rocky country because it's easier to place rebar than stakes, and the right-sized rock isn't always available. However, rebar requires more tools and may take more people and stock to install. Rocks are often the first choice as anchors because they can generally be found close to the trail. When using rebar anchors, use a brace and bit to drill the log 6 inches from the end. Place it so at least 12 inches of the log can be buried in the hillside. Drill another hole in the log a foot from the outer edge of the trail bed. Using a sledgehammer, drive a 1/2 inch by 18 inch piece of rebar into both holes until they are flush with the log or are driven to the point of refusal. Saw off any excess rebar with a hacksaw. Bury the inside end of the log a foot into the hillside and cover with the excavated material. A good anchor is especially critical on trails with steep grades or extensive horse or wheeled use. Pay particular attention to anchoring the water bar in these situations. If you choose to use rocks, make sure they're heavy enough to anchor the log. Dig a hole for the rocks on each end of the log and put the rocks in place. They must be positioned so they won't inhibit the water flow on either side of the trail or reduce the width of the trail. When using wooden stakes as anchors, cut them 18 to 24 inches long and sharpen one end. Place them away from the middle of the water bar so trail traffic won't dislodge them. Drive them into the ground at an angle. If the head of the stake frays or splits, cut it off to make a fresh surface and continue pounding. When the stake is far enough in the ground, cut the remainder off, even with the top of the water bar. One other, less common anchor method involves wrapping number 9 galvanized wire twice around the log and anchoring it to a stake. The wire weathers well, but it isn't as good as rebar, rocks, or stakes. However, there is concern about introducing more wire into the backcountry. It may be picked up in the shoes of stock. The water bar is in place, but the job is not quite finished. Runoff from the water bar can cause erosion at the outlet. To protect the discharge area, use rocks, granular material, or well-placed logs. Also, if there's a berm or if the ground slopes up or is flat at the discharge area, you'll have to dig an outlet ditch so water can flow out without running back onto the trail. Make the outlet ditch at least 12 inches wide and long enough to keep the water off the trail. After the water bar is anchored, the grade of the trail should be feathered into the excavation above the water bar. This may vary from approximately 2 feet to 8 feet, depending on the percent of the slope. It should also be slightly outsloped, approximately 1 to 2 inches across the width of the trail. Add any previously excavated clean material and additional clean fill to bring it to the right level. Compact the soil approximately 1 inch above the top of the water bar to allow for settling in the first year. Don't use any duff, debris, or other vegetative matter. Water bars need yearly maintenance to remove sediment that builds up and clogs both outlet ditches and water bars. Mud and debris should be deposited elsewhere. Clean dirt and gravel can be used to reinforce the downhill side of the water bar. Make sure the uphill grade is still feathered into the water bar and slightly outsloped. During these yearly maintenance inspections, you'll be able to tell if your water bars have been properly installed. If sediment is being deposited on an annual basis, the trail needs more water bars. If a water bar is completely filled, the angle of installation may be too shallow, or you might need more water bars.
Rubber water deflectors are basically a cross between a water bar and an open-top drain. Rubber water deflectors are relatively new and not thoroughly tested for trail use. Some forests have tried them and are pleased with the results. They found that cyclists adapt to them readily, horses aren't afraid of them, and hikers have no problems negotiating them. Also, riders of wheeled vehicles don't seem to ride up the cut slope of a trail with rubber water deflectors, like they do to avoid the bump of conventional water bars. The location criteria for a deflector is the same as those for water bars, but the installation process is different. First, the deflector has to be assembled. After determining the length of the deflector needed, begin by bolting a piece of 3/8-inch conveyor belt rubber between 2 pieces of 2-inch by 6-inch treated lumber. One edge of the rubber should be flush with the bottom of the lumber, and the other edge should remain exposed approximately 2.5 to 3 inches above the lumber. Various types of lumber can be used for a rubber water deflector, as well as treated lumber. However, logs aren't very stable in the trail and are difficult to bolt together. Solid rubber belting should be used instead of belting with fabric laminations. This keeps moisture from working down the seam and separating the layers. To install the deflector, start by excavating a 6-inch deep trench, angled across the trail at 45 to 60 degrees. Place the deflector in the trench so the wood is level with the trail surface and 2.5 to 3 inches of the rubber is exposed. Fill and pack the mineral soil around the deflector. An outlet ditch should be constructed in the same fashion as a water bar. The deflector must be long enough to extend entirely across the trail and catch all water running down the trail. To maintain a deflector, clean any debris or sediment from the upgrade side and from the outlet ditch. Reset it if it's dislodged or erosion has exposed the lumber.
Another water control technique is check dams, also known as retainer bars or steps. These are used to hold the trail tread in place and reduce the speed of water moving down the trail. They consist of rocks or a log, creating a terraced section of trail. Check dams are built of the same materials as water bars, and for the same reasons, rocks work best for longevity and permanence. But again, the right-shaped rocks aren't often available at the trail site. Rocks can be slippery when wet, and ice can dislodge them over time. Treated or peeled logs are the next best alternative, but they don't last as long. One last consideration before putting in a check dam. Wheeled vehicles find them very difficult to negotiate. If you expect wheeled traffic on the trail, consider other drainage structures. The height of the check dam is generally determined by what is required to restore the trail tread to its pre-erosion level. However, it should not be higher than 12 inches. When a series of check dams is going to be installed, stretch a string from the first to the last dam at the proper height. In most cases, the height of each dam in between will be the same height as the string. For a series of dams, it is best to place them at equal distances from one another for easier walking, especially for stock. The best length for the terrace section of a check dam is roughly the length of a horse, or 6 feet, or any multiple of 6. Place the log check dam across the trail at a 90-degree angle. Anchor the log a minimum of 5 inches into an undisturbed bank or secure it to existing stable bedrock or pins. Embed logs a minimum of 2 to 3 inches into the trail tread. Rocks should be embedded a minimum of 5 inches. If you're making a rock check dam, use only one rock to form the check dam, or no more than 2. If you have to use 2, the joints should be tightly chinked to hold back the mineral soil. Fill the rut upgrade of the check dam with mineral soil so it's level with the top of the dam, so it forms a trail grade of 3 to 5%. You can make it slightly lower in the center so water will flow over the check dam at this point. The rise of the constructed check dam step should be between 8 and 12 inches. Maintenance of a check dam generally requires resetting rocks or logs that are loose, chinking joints if material has eroded away, and replacing mineral soil in the terrace above the check dam if it's worn away.
The last water control technique we'll discuss is the drainage ditch. Drainage ditches are commonly used and very effective for springs and seeps above the trail. Drainage ditches are designed to intercept the flow of water before it reaches the trail tread. You don't need materials to make a drainage ditch, just tools for digging. A ditch is excavated parallel with the trail on the uphill side. The water will flow into and along the ditch until it can be routed to the downhill side of the trail by means of a water bar or dip, or a drain, culvert, or bridge. Feeding water into culverts is preferred over water bars because it eliminates the need to route the water back over the trail. Ditches periodically need to be cleaned of debris to maintain the desired depth.
Just a few more things. A good time to maintain water diversion structures is just before snow or heavy rain normally occurs.
Moving surface water off our forest trails isn't difficult, but it does demand careful planning, selecting the proper structure, and installation and maintenance practices.
The techniques that we've just covered will significantly reduce the effects of erosion, which in turn reduces maintenance costs, increases the safety of trails, and helps meet environmental goals and objectives.
With your expertise and hard work, you can help ensure better, longer-lasting national forest trails for the future.